Dear students, in this video we are going to study about the Lorentz force, force acting on a moving charge in a magnetic field, motion of charged particle in a uniform magnetic field, and also about the motion of a charged particle under cross electric and magnetic field.
Hi, I'm Hendrik Lorentz. Lorentz force. When an electric charge Q is kept at rest in a magnetic field, no force acts on it at the same time if the charge moves in the magnetic field, it experiences a force. This force is different from Coulomb force. This force is known as magnetic force. It is given by the equation FQ into V cross B.
About the Lorentz force, when an electric charge Q is kept at rest in a magnetic field, no force acts on it. At the same time, if a charge moves in a magnetic field, it experiences a force. This force is different from Coulomb force. This force is known as magnetic force, and it is given by the equation F is equal to Q into V cross B. In general, if a charge is moving in both the electric and magnetic fields, the total force experienced by the charge is given by the equation F is equal to Q into E plus V cross B, and that is known as Lorentz force. Force on a moving charge in a magnetic field. When an electric charge Q is moving with velocity v in a magnetic field B, it experiences a force called magnetic force, Fm. After careful experiments, Lorentz deduced the force experienced by a moving charge in a magnetic field Fm. The expression is given by Fm equal to Q into V cross B. And in magnitude, this is given by Fm equal to QVB sin theta. These equations imply the following points. This force Fm is directly proportional to the magnetic field B, and the force Fm is directly proportional to the velocity v on the moving charge. Next, the force is directly proportional to sine of the angle between the velocity and magnetic field, and the force is also directly proportional to the magnitude of the charge Q. What is the direction of that force? That direction is always perpendicular to V and B, as Fm is the cross product of V and B. So this picture gives the direction of the Lorentz force on a positive charge and a negative charge. Here the term shows the force acting on the charged particle Fm, and here also the force is downward force Fm. Next, the direction of Fm on the negative charge is opposite to the direction of Fm on positive charge, provided other factors are identical as shown. If the velocity v of a charge q is along the magnetic field B, then Fm is 0. Now we will see the definition of Tesla. The strength of a magnetic field is 1 Tesla if a unit charge moving normal to a magnetic field with unit velocity experiences unit force. So 1 Tesla is given by 1 Newton second by Coulomb meter. That's given by 1 Newton by ampere meter. Or you can also write it like this: 1 Newton a power minus 1 m power minus 1. Next we are going to study about the motion of a charged particle which is kept in a uniform magnetic field. So a charged particle plus Q is kept in a magnetic field B, and the force experienced by that charged particle is given by F, and it is moving in a circular path of radius r. It moves to velocity v. For that, let us consider a charged particle of charge q having a mass m entering into a region of uniform magnetic field B with a velocity v, such that the velocity is perpendicular to the magnetic field. As soon as the particle enters into the field, Lorentz force acts on it in a direction perpendicular to both magnetic field and velocity v. As a result, the charged particle moves in a circular orbit as shown. The Lorentz force on the charged particle is given by the expression F is equal to Q into V cross B. Since the Lorentz force alone acts on the particle, the magnitude of the net force of the particle is given by this expression summation I, Fi equal to Fm, and thus given by QVB. This Lorentz force acts as centripetal force for the particle, causing it to execute circular motion. Therefore, QVB equal to m v square by r. The radius of the circular path is given by r equal to mv by qb is equal to p by qb, as p equal to mv, the product of mass and velocity, is given by momentum. That's the magnitude of the linear momentum of the particle. If t be the time taken by the particle to finish one complete circular motion, then the expression for t is given by 2 pi r by v, as 2 pi r gives the circumference of the circular path taken by the charge. V is its velocity. Then we get the expression for the time t is given by 2 pi m by bq. So this equation is called the cyclotron period. The reciprocal of time period is the frequency f, which is given by f equal to 1 by t, so f equal to bq by 2 pi m. In terms of angular frequency omega, the expression can be written as omega equal to 2 pi f, that's given by bq by m. So these equations are called a cyclotron frequency or gyro frequency. And from this equation 3.596061, we infer that the time period and frequency depend only on charge to mass ratio, that is specific charge, that is q by m, but not on velocity or the radius of the circular path. If a charged particle moves in a region of uniform magnetic field such that its velocity is not perpendicular to the magnetic field, then the velocity of the particle is split up into two components. One component is parallel to the field while the other component is perpendicular to the field. Component of velocity which is parallel to the field remains unchanged, but the perpendicular component to the field keeps changing due to Lorentz force. Hence the path of the particle is not a circle, but it is a helical around the field lines, as shown in this diagram. For an example, the helical path of an electron when it moves in a magnetic field is shown in this figure, and the path is made visible by the condensation of water droplets inside the particle detector, which is called a cloud chamber, like this. Then we are going to study about the motion of a charged particle under crossed electric and magnetic field. So this is the velocity selector. For this, let us consider an experimental arrangement to illustrate the velocity selector as shown in that diagram. And the uniform magnetic field B is maintained perpendicular to the direction of electric field in the region of space between the parallel plates of a capacitor, which produce a uniform electric field E. Suppose a charged particle with a charge q enters the space from left side with a velocity v, then the net force on the particle is given by F equal to q into E plus V cross B. For a positive charge, the electric force on the charge acts in downward direction, whereas the Lorentz force acts upwards. When these two forces balance each other, then the expression is given by V equal to E by B, as the force due to electric field is given by QE, and the force due to a magnetic field is given by QVB. If they are equal to each other, we can get the expression for the velocity as the ratio of the electric field to the magnetic field. And this is used in the case of Bainbridge mass spectrograph, which is used to separate the isotopes. Then this means for a given magnitude of E and field B, the forces act only on the particle moving at particular speed v equal to E by B. This speed is independent of mass and charge. By proper choice of electric and magnetic fields, the particle with particular speed can be selected. Such an arrangement of fields is called a velocity selector.